A modern CPU with multiple cores is usually sufficient for small-scale models or inference tasks. However, for training larger models, a CPU with higher clock speeds and more cores can significantly reduce the training time. The amount of RAM required will depend on the size of the dataset and the complexity of the model. A minimum of 8 GB of RAM is recommended for smaller models, but larger models may require 16 GB or more. GPUs are highly recommended for training deep learning models as they can significantly speed up the training process. A mid-range GPU with at least 4 GB of memory is recommended for most deep learning tasks. Sufficient storage is required to store the dataset, model checkpoints, and other training-related data. A minimum of 256 GB of storage is recommended for most models, but larger models may require more. A quick look at the architectures of the CPU and the GPU can guide us into understanding the different models they can support. A CPU is good for smaller models with low latency and that require a higher precision. A GPU allows for high parallelism and throughput and gives you good precision, but it has high latency. Nonetheless, GPUs offer higher speeds in the deep learning training tasks. The result of the code to the right is the comparison of performance between a GPU and a CPU for a machine learning image recognition filter task. You'll notice that speedups of 35x are easily achieved with a GPU over a CPU. Edge devices need different data types, interface to different sensors, and the ability to run multiple types of workload. These smaller edge devices must run AI platforms on various power modes to conserve battery. In the small real estate of the smaller edge device chips, how much performance can one get? The smallest area may not be the best if it does not provide the required performance. Performance requirements are measured in tera operations per second, or TOPS. It is important to measure entire network performance instead of just the peak TOPS. For various markets, Cadence Tensilica provides IP including intelligent sensors, IoT audio DSP, and IoT vision DSP. The graphs above show a comparison of performance of the ResNet 50 model over different hardware or target platforms. When selecting the hardware or IP, for the same selected model, the number of inferences per second is a performance metric that is used to compare devices. Instead of a CPU or a GPU, you could use custom IP like Tensilica Vision DSP, or Tensilica AI Max that gives you better performance. Along the lines of Cadence Tensilica AI Max, ARM Neural Processor IP, and Google Tensor Processing Units also offer performance that is magnitudes faster than a CPU or a GPU for the larger neural network models. These neural processing units and tensor processing units use multiply accumulate or max to process the multitude of matrix multiplications required for the neural network models. Building your own AI chip requires scalable accelerator engines, scalar and tensor processors, and on-chip memory, or off-chip memory such as DDR, GDDR, or HBM. You also must collect and process data from the sensors, support various interfaces, and meet security, safety standards. Depending on the size of the models, a lot of datapath components are required to compute the output of each layer. The larger the data and the model, the more hardware is necessary to store, transfer, process the data to accelerate machine learning applications. To store the parameters and weights, you can use on-chip DMA, off-chip memories such as DDR, or stacked die memories like HBM. Each memory option comes with its own set of challenges. Cadence Denali memory and storage IP solutions include DDR, LPDDR, GDDR, HBM as robust hard fizz or firm fizz. When building these custom chips, one must account for the power requirements by the different components. On high bandwidth systems, the interposer, which is a large network of buses, can dissipate a large amount of power just from moving the data. Designing the interposer is also a challenge that one must be ready to face. Here is an example of custom hardware for automotive applications from Mobileye, used for object detection via a convolutional neural network. The custom hardware includes a general compute accelerator, a CNN accelerator, multiple CPU cores, and a LPDDR built into the same package.